For our exposure, we learn through building products, and some of those applications that we'll talk about in today's session, and we learn how what is the core idea behind the architecture of those models, right? So yeah, so before we start talking about the stable diffusion, I think it's important that we talk about what has been the journey on AI generated art. So it's not something that has come up just now. AI generated art is there for a long time. Last decade was very much in talks of GANs only. So GANs are generative adversarial networks, and we look at the basic structure also of the GANs. But this is something with which a lot of us have already experienced some art generated by AI, but those architecture were GANs. So and before GANs also, there were architectures like VAE, variational auto encoders, and so variational auto encoders tried to generate some of the diverse artwork, which was getting challenging because of the way they get their information to a low dimensional space, and then from that low dimensional space they want to upscale that data. So but there were a lot of challenges involved there. So I'll just try to share my screen and try to connect it with my pen. Am I able to share my screen? Can you guys check my tab also?
We can't see your screen. Like GANs is visible, but the other screen is not.
Okay, I'm facing some issues connecting to my notepad. I'll just try it one more time, otherwise we'll just proceed with the presentation.
Yeah, it's visible.
Perfect. Okay. So let's just talk about how the data was getting generated mostly in the last decade. One, the very early idea was VAE. They would simply take data. Let's consider images for now. They would put it into a low dimensional space. They would encode it, and then the decoder would decode it, right? So this is encoder, which would basically get your high dimensional image to a low dimensional object, low dimensional vector. And then you could make changes in this low dimensional vector, and the decoder would produce something new. This was the very basic idea about what VAs were. And then GANs came, right? GANs again had very interesting setup. I think in terms of the setup, the idea is very interesting, that you basically have two models in GANs. One is called generator model, another one is called discriminator model. And both the models are competing with each other because they both target opposite loss functions. So if just to check the example, so let's just check out this website. This person does not exist, right? Every time you refresh this page, you get a new image altogether, right? All of these images are fake images. And the whole purpose is that they are getting generated through GANs. This is why you wanted to see this. And So how this GAN is producing so many images, right? So what it does is that this is how the model gets trained. The generator model would always try to produce a new face. So you give a random vector, basically a seed to the generator model. It will take that seed and it will try to generate uh, an image out of that seed, right? This is what generator model would do. And then you would give that generated image and an actual face also, which is the real example, which is your training data, to a discriminator model. And then discriminator model would try to differentiate between which one is a real, which one is a fake, right? And whatever decision it takes, basis that decision, you update the weights for both the models. So, and you update it in a way that discriminator becomes smarter in differentiating which one is real, which one is fake. And you update the weights of the generator in a way that generator becomes smarter in producing more fake faces, but they look very much like the real faces, right? So they both are competing against each other. And discriminator tries to become more smart by building a smarter classifier that could detect which is a real image, which is a fake image. And generator would again try to update its weights in a way that it is able to produce fake images, but very much real looking, so that it tries to fool the discriminator, right? And then you eventually reach an equilibrium stage where both the models are decent smart. You're not able to reduce the loss further, and that's where you stop. And then you take the generator model out of this loop and put it into the production. So when we saw that website, this person does not exist, it was the generator model that was drawing that inference every time we were refreshing the page, right? It used to take a random seed, and from that random vector, it will generate an image. This is what is basically happening whenever we are refreshing that page and we are getting a new face. Yeah. But then again, GANs also had some issues. A very prominent issue with GANs is vanishing gradient, which is basically you reach a point wherein your weights stop getting updated. So let me just again use my notepad for this. Just a quick check. My notepad is visible, right?
Yes, it's visible.
So how does the weights get updated, first of all, during that back propagation that we have while our training is happening, right? So our weights, our new weights are basically our old weights, and then you adjust your old weights by some factor, right? So this is that factor. So our new weights is basically old weights minus this factor. This factor is basically the gradient, the change in your loss function with respect to the weights, right? This is that gradient, right? And then you multiply that gradient with a learning rate also, so that to speed up the process. But the point is that it depends on this gradient, right? The rate of change of the loss function with respect to the change in the weights that you do, right? But this is a little complicated to calculate, because when you have a model, and especially generative models are a little complicated. They have a lot of nodes, they have a lot of weights in them. The parameters are a lot, right? So change in loss function with respect to the change in the weights is a little difficult to calculate because there are so many weights, right? So you use that very basic differential law, the chain rule of partial differentiation. So in order to calculate this, what you do is that you calculate the rate of change of the loss function with respect to each node, and you take a product of it, right? Which lets you calculate this, right? But the rate of change of loss function with respect to each node is so small. And when you multiply that gradient for each node with each other, the end number that you get here is very, very small, right? And then you end up in a situation where this number is so small that it is close to zero, and your new weights are as good as your old weights, right? So because you have increased the node so much that the learning has stopped to get transferred to the back of the nodes, right? So this is the issue that's called gradient, vanishing gradient, a major issue with the GANs. And then there are some other issues also. There's mode collapse also. Mode collapse is again a situation specific to GANs wherein, so what's happening here is, if you look at the basic architecture here, the generator is trying to do something that discriminator can't discriminate, right? So what happens if generator keeps on producing the same kind of object that discriminator is not able to distinguish? So maybe you are trying to produce, we all have seen handwritten digit images data set, right? Where you have 0 to 9 numbers written on handwritten in a handwritten way on images, right? Maybe you're trying to generate a GAN that produces a lot of images of that kind of data set, right? But then you could end up in a situation where your generator is only producing zeros or ones, because that's easy for him to learn, and discriminator is also able to pass those images through, but it is not producing other integers like 8, 9, right, 7. So you're stuck in a situation where the generator is producing same kind of results again and again, right? That's called mode collapse. And so these were some of the issues. And again, the biggest drawback with the GANs was that it was difficult to produce variety of results. So the diversity was very much lacking. Just to show you a quick, we'll just quickly pull up an example. So the idea with the GANs was that GANs was really good when you have to preserve the structure and just change the style of the images. They were very good at it. We all have seen face app old images, right? Old man images. So yeah. So you look at these pictures, right? So this is also GAN. This is style GAN too. But what these guys have done is basically they have trained a generative model that adds that effect on that image that makes you look old, but it keeps the structure almost the same, right? There's another popular app called Toon app. If you look at this app, so I'm just trying to give you examples how these generative models were being used. We all must have used these models through apps. We didn't know that they were GANs or style GAN, right? So you look at this image. What this image has done is basically have taken a real life image and produced another image, right? They've preserved the structure, but changed the styling of it. So these were the kind of problems where the generative models were doing well. The GANs were doing particularly well. But when it comes to adding a lot of variety in the data set, that's where they failed. That's why it was getting difficult to scale the generative models. Yeah. Okay. So then now we are done with GANs also. We understood VAE also. So now let's come to the talk of the town, which is stable diffusion, right? So by the way, all of these images are mine images. Even the image that was there on the first slide, that was also mine. And all of those images are AI generated images. As in, of course, they look like me. The face structure is, again, the structure is pretty much the same, but there's a lot of styling added to it. And all of these images have been created using the stable diffusion. And as you know, stable diffusion needs a prompt also to generate the art. And we'll see that in some time, how does that all work? But yeah, the whole idea is that now let's talk about what is stable diffusion. How does, what have they done because of which they have produced so much diverse results when we compare it to GANs. Yeah. So for stable diffusion, let's just first understand what is diffusion. Okay. So yeah, let's just first understand what is a diffusion model. Basically, stable diffusion is basically nothing but latent diffusion model, and we'll understand that also. These are latent diffusion models with some conditioning. Conditioning is that you add some textual context to it through text embeddings, and you put them through a classifier, which is basically helping you to focus more on that prompt, right, through that guiding scale, right? So these are small components, but the major component sitting at the center of stable diffusion is again the diffusion model. So this is how you train a diffusion model. Again, very simple to understand. You basically take images. By the way, stable diffusion is trained on Lion 5B dataset, so which has 5.83 billion images with text embeddings. So this is the kind of data that you would need if you want to train something from scratch and build something like stable diffusion. Stable diffusion is not the only player who has been able to do this. OpenAI has released DALL-E 2, Google has released ImageGen, Midjourney is also there. All of these players have released their text-to-image models, and all of them are based on diffusion model. Like the core is diffusion, And then again, there are small components in the whole process that are different. Somebody is using a different kind of an encoder, somebody is using different kind of scheduler to add the noise to it. But overall, this is how these companies have been able to produce such good results because of the diffusion model technique that we are going to learn now. Only good thing about stable diffusion that we all appreciate is that we all should appreciate is that they have made their weights public. So you, me, we all could go and download their weights, the model weights, and we could run those model on our local machine also. If you have a GPU of 8 GB VRAM, you can easily run these model on your local also. If you don't have it, you can put it on Google Colab and run the same model, right? But that's what the major breakthrough that has happened 5 months back when Stable Diffusion released their model. They made their model open source, and all of lot of applications in the market, a lot of use cases have started to build on top of Stable Diffusion, because it's difficult to build a diffusion model. But then if you have the weights, you can fine tune it to do something. So for example, Lensa is using Stable Diffusion only, but they are using it for a specific use case to produce your avatars, facial avatars, right? And that's how, and then there are other applications also. Somebody is using Stable Diffusion to produce the product creatives that you can directly upload on e-commerce websites. So use cases are endless. Basic Stable Diffusion is very versatile. It is already good. In a lot of cases, you don't need to fine tune it. But if you have a specific use case in your mind, if you have a specific business problem that you would want to solve that involve images, creating images, aesthetic images, then you can fine tune the weights on any dataset that you want, right? Okay, so let's talk about diffusion model now. So this is how it works. Diffusion model has 2 ways, forward and reverse. This is how you train the whole process. First, in the forward diffusion process, you take the input image and then you keep on adding noise to it, right? And you keep on adding noise to it till the time you're not able to comprehend the image at all. It is very noisy. Okay. So this is time step 0, 1, 2, 3. So timestamp is something that you would see everywhere, but that has nothing to do with the time. These are just the understand it as a step, first step, second step of adding noise to it, right? And the way you keep on adding noise to it is controlled by scheduler. So that's where you get a lot of play around with different ways to play around with the existing model also. You can change the schedule, you can make it exponential also, or you can keep it linear only. That way you can keep adding the noise in a linear way. And in an exponential, you won't add much of the noise in the initial steps, but you would add a lot of noise once the image is already a little bit noisy, right? So this is the forward diffusion process. This does not involve any AI. You can simply write any logic that would keep on adding noise to a series of steps, and you would make an image noisy. Okay, so this is forward diffusion. Then in the reverse diffusion, you would train an AI model, again a deep learning model, that would basically take you back from this noisy image to the original image. Now, this is where our model is there, which is here it's called denoising UNet. UNet is again an architecture, a very old and very prominent architecture. We'll talk about that also, but for now, let's just consider it as a black box model, a deep learning model built on convolutional layers. And you train that model in a way that when you give it a random noise, it is able to give you back the original picture. There's one catch in it, that in diffusion models, they don't predict the actual picture, because it's a little difficult also to predict this picture out of this whole bunch of noise, right? So they do it in an iterative process, which we'll see in the next slide. But what they predict is not the original picture. What they predict is the noise, right? So this model is not predicting this image. This model will give you the noise present in this picture, and then you must subtract that noise from this picture to get to here. Okay. So the only catch is that you're not trying to generate the complete good picture that you had at time step 0. You're not trying to generate this from this noise. You're basically trying to figure out the noise present in this picture. And then you keep on subtracting that noise from this picture in a loop, so that after some steps, you reach a point where you have a good looking picture. Yeah. So for now, simple steps: forward diffusion, reverse diffusion. Forward diffusion, you keep on adding noise to it through some scheduler, do not require AI. In the reverse process, you basically train a model that takes in this image, the noisy image, and tries to predict the noise present here. And when you subtract that noise, you should be able to get back to here. You can use any simple loss function. You can use mean squared error. That's what being used in the latent diffusion model also later on. But any simple loss function would get the job done. Yeah. So this is diffusion model. But we saw that this particular model was built on the structure called UNet. Right? UNet again has a very good history. You might have seen instances where you would want to generate a mask out of any image, right? You would want to identify the presence of some object. And UNet was particularly built specifically for biomedical images, where you have X-rays and all those things, and you would want to spot the infections or maybe some particular region in that X-ray. Right. And then, of course, it got pretty popular. Then whatever instance segmentations or semantic segmentation models that you see, most of them were built on UNet initially. Even today, UNet is being used a lot. Right. But the whole purpose is just to show you quickly what, because this will give you a better idea. Image segmentation, basically it's semantic segmentation, because it tries to preserve the object, right? So this is how you would get the image, right? So you pass in a real image, right? For example, here, if you look at, or let's just pick up a simple case. These are all basically instance segmentation, where you see different classes segmented. That's the difference between instance segmentation and the normal segmentation, in which you have only two classes that you're predicting. So consider something like this, where you have this image and you want to find out an object. So you would want to generate that mask, right? This is called a mask, right? So this was the initial use case for UNet when it was launched. You wanted to give the actual X-rays here, and just a sec. You would want to give actual X-rays here, and you would want to predict the infection areas in that X-ray. Yeah. Okay. So very basic structure. Again, it's, first of all, it is fully convolutional. It does not involve any dense layers. So you're given a picture, you take it through series of convolutional blocks, and you do max pooling also to reduce the size, right? And once you have reduced the size of your initial data to a very dense vector, from there you would again upscale your picture, right, through a series of upscaling techniques. So here, basically, what is being used is transpose convolutional layer that is being used here to upscale the image. But the core idea is UNet, as it looks like a U also. It is, this part is called encoder, this part is called decoder. First, you encode the image to a low dimensional space, and then you expand your low dimensional vector to a high dimensional vector. The idea is to get back to the original size. That is why you would see in that picture also, the picture that you gave for the image segmentation, the mask was also of the same size. So what it basically did, every pixel in that original image, it classified that every pixel in that original image to some class. Maybe if there's a horse present, if that pixel is a part of horse or not. So maybe if you are giving it an image and you would want to do a segmentation for horse, right? So what the model will do, it will tell you for every pixel if there is a horse in that or not, or if that pixel is a part of that horse or not. So every pixel would be classified as either white or black. So maybe all white would be there for horse, and everything rest of everything would be for black. So I'm trying to give you a basic idea about how the image segmentation models are used, and this is the initial use case of the UNet model. But again, the structure is very widely used in different use cases. In the diffusion model, we are using it for a completely different purpose. But again, the size is constant, right? So whatever the size of this noisy image is there, the prediction that we are making is also of the same size. That is why you see wedge here, and so contraction here and expansion here, because you would want to reach to that same size there. Yeah. So this is how a typical UNet looks like: series of convolutional and max pooling layers that reduces your image first, and then you upscale it using transpose convolutional layers. And also you would see there are connections made inside the encoder and decoder also, right? So you could see this also, this connection also. So these connections are nothing but what you're basically trying to do is that you are concatenating the results here. So what the output of this layer is, you are concatenating that with this layer, the output of this layer. So this layer output and this layer output would be concatenated here. So the idea is that you are concatenating the outputs of the encoding layer to give more information and to preserve the information, basically. Okay. So because when you are expanding or when you are decoding from this low dimensional space to high dimensional space, you would want to retain a lot of information which was originally present in the image, right? And for that, you give a lot of shortcuts also. These shortcuts are nothing. You're just basically concatenating what information was available there and making it available to the upscaling models also. Okay. Upscaling pipeline also. Okay. So simple. Yeah. Okay, I'll continue. Maybe we can take the questions at last, or we can take it now also. Okay, let's do it at the last. So this is the basic structure of the UNet, right? So let's just see how stable diffusion is built now, right? So stable diffusion is the same model, the same diffusion model, everything that we have learned up till now. The only change here is that instead of working with the images, now we are working with the latent vectors, which is basically the dense form of that same image. So the issue was, while you were trying to work on this, the major issue was it's very difficult to train a model that could detect the noise present in a 512 cross 512 picture, right? And to train it for a versatile data, you would need a lot of training, and it's a very difficult task basically to achieve that because of the size of the picture. And consider if you're doing it for heavy pictures, it becomes more and more difficult. The number of params that you add, if you go from 512 to 768 or maybe to 1024 cross 1024 pixel image, you add a lot of parameters to it, right? And then trying to do something that is taking the complete picture as an input, it involves a lot of weights and parameters that you will have to fine tune later on. So what stable diffusion did, so they came up with the concept of latent diffusion model, right? The concept was, the concept is not originally their invention, but the way they have implemented is for sure. So what they do is that instead of running the diffusion training on the original image, they do it for this latent data. What is that latent data? For every image, you run it through an auto encoder decoder, and you compress that image to a latent data, right? And you use the encoder decoder to get your image back in the original form also. So whatever training you do here, you do it on latent data that you get by encoding the image, the input image, right? And whatever output you get, you again use your decoder to get back to the image, right? So it's the same thing what we were doing here. Instead, the only change is that instead of the images, now we are using the latent data, which we are getting from auto encoder decoder, right? So this was one big change in stable diffusion, because instead of using that whole picture, they started to use those latent vector, which reduced the size of the model significantly, even though even now the model is on like roughly 8 to 9 GB. So consider what the size of the model would have been if we would have been playing with the original images, right? So this is how in one way they reduced the size of the model and made it fast, right? And second, another thing that they did was the conditioning. So they added a guidance onto that image generation process. So right now, all we have seen is that how do diffusion models or maybe latent diffusion model create images, right? But we never talked about how is it creating or what is it that is guiding the model to create maybe a cat or a dog or maybe whatever the art that you want to generate. So just to get a kind of little idea about, yeah, Lexica. So this website is basically a good repository of all of the artwork that's AI generated. It will give you a lot of good artwork along with the prompt also. So maybe after, if we get the time to go through the code, we can use the same prompts and try to see how close are we able to get to these images. But I'm sure you would enjoy these images. And it's fascinating to know that all of these images are AI generated, right? And so, for example, this prompt, oops. So yeah, for example, this prompt was used to build this picture, right? So where does this prompt come from, right? We haven't seen that thing yet, right? So let's just talk about that also. Yeah. Okay. So the same thing. It's just that now what we'll do, you remember that we were giving the latent data here. Latent data, this latent data was the representation of the noise only, right? But with the noise, now we would want to give one more information, which is the textual data or the class of object, right? So this is how you do it. You basically add a text encoder also, and you pass your prompt through that text encoder, and you basically build text embeddings. And in your diffusion process, again, that same process, instead of just giving the latent noise that we were giving before, now we'll also pass the text embeddings. Okay. So, and again, so stable diffusion, by the way, uses Clip, which is also being used in the chat GPT also, but you can use and you can play around with different text encoders also and see which one works best. Though I think BERT would give you very good results because of the sheer mass on which it is trained. But anyway, the point is that you need a text encoder that could create text embeddings for you, which you could give to the diffusion model along with the image, the noise that you were giving in the latent dimension, right? So everything is same, it is all same, but you would also see that this Q, K, V are nothing. These are just those embeddings also. But so you remember how our UNet structure was built like, right? So in the UNet, when you were giving those shortcut callbacks also, these callbacks also. So here also in the diffusion process, you would give the same text embeddings there also, right? So it is basically the diffusion model wherein one, you are not giving the actual images. Instead, you are giving the latent representation of those images that you get through encoder decoder. This is the decoder. Second, so I think, yeah, this is a better representation, like easy to understand. So this was the simple diffusion process, right? Image in, noise out, then noise in, the same noise in, and you would want to predict the noise present here so that if you could subtract that from this, you could get to the original image, right? Simple. The changes are, one, instead of giving the original image, you have started to give the latent representation of those images using the encoder and the decoder, right? And you add the noise through the scheduler that you want. And then while in the reverse process, you're not just giving it the latent representation of the noise, you're also giving the text embeddings also. Text embeddings could include the prompt also, it could include the class of the object also, but you could get textual guidance also to it, right? And then you train it over it. So this is the major difference. But then, and there's one more catch to it. If you would have used any of the web UI tool, you would have seen few parameters while you are training them. For example, maybe we can just check Dream Studio. we'll also try to go through the Jupyter notebook once, so that we could just see and it's not that because the Hugging Face already has very clean, good, lot of resources available for you, and especially for stable diffusion, you would easily find a lot of notebooks that you can simply play around with, where they would download the weights, and you can run the inference on Google Colab easily, and then you can play around with other aspects also of stable diffusion, right? So this is a typical, so this is the official studio of Stability AI. It's still in beta, but let's just try to do something. And then later on, let's just try to go through the Jupyter notebook also once before the time runs up. Let's just pick something. Maybe this. Just copy the prompt. Yeah. So first it asks about what is the width of the image. You can control that. Let me just pull it to 768 cross 768 CFG scale. This is the guidance scale. Now, this is a very interesting concept. Guidance scale is basically a way to tell the diffusion models how much of attention or how much of weightage to give to the prompt. So you remember how so let's just use my tab also one more time. Guys, I hope the tab is visible. If it's not visible, I would request the moderator to directly cut me in on the call and let me know.
Yeah. There is a little bit confusion. I guess we are also answering the questions, but you can view both the screens simultaneously. There is an option called View option on the top of the screen, where you can see two names, Akshit Raja and Akshit Raja. You can switch the screens. Whenever he is like explaining using tab, you can switch the screen. Thank you. Both the screens are visible simultaneously.
Right now they're available?
Yeah, they're available. Both the screens are available.
Perfect. So about the guidance scale, we wanted to check how does the guidance scale work. So basically, we remember that our diffusion model basically would give the image basis. This is the output, right? This is the output image, and what input that it takes. It takes basically the latent representation of the noise, right? And it also takes the text embedding. This is the text embedding, right? And it would also say the noise basis the time. Time step is basically nothing, the t time at which you're adding the noise, right? So it's representation also. So basically the noise, the text embeddings, the class embeddings, and the image noise, right? All getting into the diffusion model, and the output is we're getting a image, right? So though we get the noise also, and then we subtract that noise from the input noise, and then we get our output image, right? And we keep doing that in a loop till the time, and that is what they ask here as number of steps, right? How many steps do you want to run it for? Like how many times do you want to run that loop where you predict the noise, subtract the noise from the input image, and then again predict the noise, then again subtract that noise from the input image, right? You run that loop till the time you get a good image, right? So this is the number of steps here that we can see. Now, the thing is that CFG scale, which is a guidance scale. So what you do here is that you basically have every time it predicts basically two outputs. It's not producing one output. It's producing two outputs, one with the prompt and one without the prompt. Right? And basically consider CFG scale as a number that defines the weightage that you would want to give to the image with the prompt, right? So every time it is generating an image using the prompt, it is basically generating two images, one with the prompt, one without the prompt. And then, so technically how it works is that it basically takes the difference between, so we saw that how the loop works, right? You given an input noise, right? You give it input noise, right? To be, this is our big model, right? And it predicts, right? Output noise, right? This is also noise, right? And you subtract that noise from this picture and it gives you a better picture. This is a better picture, right? And then you keep on doing this, right? So what you subtract here, this is also multiplied by a constant, which amplifies how much do you want to subtract it, right? And this constant is basically a guiding scale, right? And this constant is also basically what this constant is. This constant is the difference basically between those two images, one with the prompt, one without the prompt. So basically you try to predict noise, right? And then because you have two images, one with the prompt, one without the prompt, you calculate the difference between them. So maybe that difference is X, right? You amplify that X and subtract it again from your output image, because you are basically punishing your model too much if there's a too much of difference between the image with the prompt and without the prompt. So to understand it, like in simple terms, let's just say if you increase the scale too much, it will try to relate very much with your prompt. Okay. And if you keep it a little low or medium, it will try to maintain that balance. It will try to print those aesthetic pictures also, and it will try to match that prompt also, right? So there's a balance that you have to create always, right? So, and with almost with every parameter here that you see, there's a trade-off that you have to take. You can increase the width size also. So you can increase the width of the image, height of the image. It will take more time for you to generate because it's an iterative process, right? Diffusion model is an iterative process. You have to run it for X number of times, right? And you run it for every pixel, right? Not for every pixel, but you're trying to generate that noisy picture, right? So for every pixel, you have to do that calculation, right? So more the size of the image, more the time it is going to take. CFG scale also, you have to be in a very much of a balance. You don't want to keep it very low that the image doesn't resemble the prompt that you have given it. And you don't want to take it so high also that it is matching the objects, but the image doesn't look aesthetic or it doesn't make sense, right? So that way. Next one is the number of steps. So just a second. Next one, number of steps. How many times you would want to run that process? More number of steps, more time it is going to take. Images is just that how many images you want to choose, right? So let's just create something and see. And then later on, let's just try to check the notebook also quickly. Till that time, I'll just try to download the weights. This is the notebook that I downloaded from Hugging Face. I'll share the link of this notebook also. And then you can simply run it on your collab also. Yeah. Just make sure. Yeah. Just making sure that the GPU setting is on. And then let's just connect. It's a very simple notebook. Basically, we'll not be doing much with it. We'll simply connect it with our Hugging Face account. Second, we'll download the weights of the model. We'll download the complete pipeline. The pipeline will ensure that we don't have to do much when it comes to processing the input, loading the weights, running the inference, and then processing the output also. Everything would be managed by the Hugging Face pipeline. Till then, we can go back and check these results also. Okay. So these are the results that we created on the official dashboard, right? So these are the images that we are able to generate using that prompt, right? So it's kind of cool, and you would see a lot of content that is getting generated on using the AI on social media platforms also, and also in the business case now. So going forward, prompt engineering, I think, is going to get a little big. A lot of attention is going to go in prompt engineering because ultimately you have played around with these params a little bit, though we haven't done much. We have kept it as the standards. And this is where your major effort has gone into in order to write and think of a prompt, right? So, and not just with the stable diffusion, I think even with the chat GPT also and other generative AI that we are going to see, the input that you are going to give is going to define the quality of your output, right? So prompt engineering is also getting a lot of interest uh, in terms of in the data science community also and in non-tech also, because it's not that difficult to understand. It's more of testing. So you would see some keywords also that are added into this, right? And we'll see that in the Jupyter notebook also. And there are other applications also of the diffusion models that we'll just see in the notebook. But the core idea is that the prompt engineering, the prompt that you give, plays a very big role in the kind of art that you are going to get. And if you browse the lexica, you would see the prompts. All the prompts have some keywords that are very frequent. For example, super rich, paper, frog, luxury, blue, crystal, gray, right? So luxury, blue, crystal. So you can add a lot of artist names. You can add styles. So Stable Diffusion is already trained on a lot of artwork, and it understands those classes also. It understands the uh, styling also. It understands the styles of a lot of painters also, right? A lot of artists also. So you can mention those artist name also, and it will try to generate the art in that artist style only, right? So you can maybe Da Vinci, you could write, give the style name of that artist, and it will try to generate the art in the style of that artist only. So a lot of things that you can do with the prompts only, right? Let's just come back here. Now is the time that we run our, okay, we have to first give the credentials so you can create a free account on Hugging Face. You need to give your token just to add the certificate. Once you're done with that, I'll simply download the pipeline. It will download all the weights that I need in order to run the inference, right? Let's just run them. And that's it, because we have downloaded the whole pipeline. So we'll simply play around with the prompts now. By the time it is downloading, let's just copy the same prompt and try to build the same thing here also. You might face a little bit of inconsistency in the quality because here the size was 768. What I'll be doing it there was what we'll be doing in the Jupyter notebook is 5112. Let's just change the prompt here. We have the weights now. No need to. Let's just see. Seed is something that you, and I don't know if we saw the seed here. So this is not giving an option to set the seed. But we know seed is important because seed defines that noise at the start, right? So if you look at this process, right, this latent representation of the noisy image comes from the seed, right? And so seed basically preserves the core structure of the picture, right? So this is also important. So while you are playing around with the prompts, try to play around with the seed also. And once you have found a good structure of the picture, and then you can keep the seed constant and play around with other factors, right? So yeah, we got one picture. So decent looking. So this is how basically you can change the seed, run more time also. A few things that you would want to see what happens if we play around with those steps, right? We could do those things here also. Here you have a very good GUI, so you can simply reduce the number of steps. Let's just reduce the number of steps to just 10, okay, and see what happens. And let's just try to do the same thing here also. Here, because they didn't allow us to go beyond 10, but here we can do that. We'll run it for 3 steps and let's just see what happens, right? So this is the thing is, what do we expect? What we expect the picture is that picture won't have good quality, not sharpness, because we haven't run it for a good number of times, right? So what would have happened? we would have taken that noisy picture, predicted some noise, removed that noise from the noisy picture, again predicted some noise, removed that noise, right? And with some guidance scale also, we would have amplified the number that we are subtracting also, right? So these are the things that we have done, but we didn't do it for enough number of steps. That's why we didn't get that clear picture. Let's just do the same thing, but this time let's just do it for 30 steps. So now you can see that the features are pretty much sharp and you're able to relate, because the more the number of times you do it, it tries to refine that. It tries to find out the noise and then subtract that noise and sharpens your picture more, right? I think on an average, somewhere close to 25 to 50 is good. 25, I think, is a good number. I think that's the default also. Let's just check here. I think, sorry. Okay. Yeah, I think 25 is a good number for to start testing. And then if you want, you can increase it as per what you're trying to create, right? So this is how we saw what is the impact of changing the steps when it comes to generating art, right? Second is your classifier guidance. This is again that same thing that we were talking about, right? What is the weightage that you would want to give to your prompt, right? So here also, I think the default number is 7.5, but you can take it up to 20 something. I think better way to play around with this is the UI, because it's good, and you get some free credits also every time you register through a new ID. So CFG scale, I think maximum is 20, yeah, but I think 7.5 is good enough to start with. Let's just, so what we are basically doing is that we are copying our prompt 4 times, and then we are printing the output with different guidance scale, 1.13, 7, 14. And let's just see what happens, right? So I already have some outputs available with me. And there you could see that in general, the quality would improve as you go from here to there. It would try to match more on your on the prompt, basically. Yeah. So I think this is not making much sense. Even this is not making much sense. This does make some sense. It is close to the prompt also, and I could see the structure also good, right? This is also fine, but here also, these two, the faces got distorted a lot. These are a little better, right? So again, the idea is that you can play around with the guidance scale. The initial idea is that initially it will try to build something wherein so the low CFGS scale, the low guidance scale would try not to give too much of importance to the prompt, and it would try to generate a good aesthetic image. If you give too much of weightage on your prompt like this, right? So it will try to adhere too much about the prompt and might lose the creativity in that image, right? So you would want to find a balance wherein you are trying to match the prompt also, but you're not going absolutely on the prompt and not on the aesthetics and the creativity, right? So there's a balance that you'll have to maintain, right? And then there's something called negative prompts also. So again, there are small things that you can do with it. In negative prompt, you're basically what you're doing is I won't run this because we're getting a little short of time. But but the idea is that what we do is that you subtract one image from another image this time. So basically, Labrador in the style of Wormer, this is what it printed, right? For this prompt, you would create a negative. If you give it a negative prompt also to the same prompt, you can add a negative prompt also. If you give a negative prompt, then it would create an image for this and it will subtract that from this image, right? So negative prompts are very important, especially when you are deploying some application and you're giving that application to the user's hand, and you would not want to the model to print NSFW content, or maybe you would want to restrict some scenarios, right? So that is where negative prompts help a lot, and everyone would if you are going into production, if you are putting this in any product that faces the consumers, you would want to the scenarios that you do not want the user to face, you can prevent all of those scenarios through negative prompt, right? So, and this is another functionality. So you remember the model, right? The model we started with the latent representation of the noise, right? But instead of that noise, you can give it a basic picture like this also. With this picture, you have basically told the model not to start from the noise, but to start from this picture. So it knows the basic structure of that thing of the image that it wants to create, right? And with this input image and the text prompt, it is able to generate this, right? The code is very simple. I'll share the notebook also, but the core idea to understand is that what you are doing is that you are playing around with the seed that you give initially, the noise that you give initially to the diffusion process, right? You control that. You can give it a random noise. You can give it a structured image also that has some structure in some form. Second, you can play around with the textual prompt, right? You can play around with the keywords. You can play around with the class. You can do all those things, right? Then you have the negative prompt also. If you want something not to appear, you can play around with that negative prompt also, right? And then there are other factors also that you can play around with, right? There are a lot of other things also that are not here, but they are very easily available. You guys can have a look at them. Basically, so what happens is that you guys have seen this application called Lensa and a lot of other AI avatars also, right? So these are also built on stable diffusion only. And what's basically happening is that they are fine-tuning the base stable diffusion model for a subject. So for example, I want to create my avatars, right? So I would I would basically fine tune the stable diffusion weights with my few of the images. And I would introduce me as a subject to stable diffusion. And then I can create the artwork for myself also. So it would understand my subject also that I've created for. And then image inpainting also is something, if you don't want some part of the image and you want to remove that part of the image and ask the diffusion process to generate a new part of the image, right? So suppose you have a picture in which, so let's just take an example of this only, maybe this picture, right? And I don't like basically maybe the small tree that is coming here, or maybe I don't like this block, okay, which is there in the image. So I can basically remove this part and ask the stable diffusion to generate a new part of the picture for this. So this is called inpainting, right? So you can do inpainting also using stable diffusion, right? You can upscale your images also. You can do image resolution enhancer also using stable diffusion. So there are a lot of image editing related functionalities which you can do while using stable diffusion. So yeah, guys, that is it. I think that is it for this session. We have covered basically the overall structure, just a broad overview of what the model looks like, what is the core components of this model. And definitely there's a lot of scope. If anyone wants to play around in the research, there's a lot of area when it comes to, you can fine tune this existing model for any niche, for any business use case. One, you can do that. You can play around with the embedding structures also. You can change the embedders also, right? You can play around with the scheduler that adds noise, right? You can play around with the this diffusion UNet also. Maybe you can play around with some other architecture that preserves the size, because size preservation is important, right? The size that comes in here and that gets out here are of the same size. But you can play around with the structure. You could use some other architecture also, right? So that's how you can play around, and there's a scope of good. There's a scope of doing more research and playing around in the existing structure also this way. Yeah. So with this, I think we'll end the session today. Thank you very much, guys. If there's anything we can quickly discuss, we can do that now.
Yes, yes, sir. Before we kick off the things and hide it over, like we have put up one feedback poll. So I'll request all to fill that feedback poll, and we can start the Q&A session.
Guys, just give me a second now.
Yeah.
Yeah, guys, anything? Otherwise, any question that we can quickly connect, discuss. Otherwise, we can connect separately also. You guys have my LinkedIn connect. Feel free to connect. Uh, and if you have any idea around stable diffusion, wherein you would want to, where you would want to serve a specific niche, where you would want to, so any business problem, any research problem where you need images in a particular way, we can use stable diffusion to fine tune the model, fine tune the weights, and basically serve that business case. Yeah.
There are just 2-3 questions in Q&A section. Can you see it?
Yeah, so Puna Kameswaran, the question is, in the PPT flow diagram, we have the original image, which is then compressed to the latent form. Okay. However, in the inference notebook or the Dream app, we never gave any input in image input. We just gave the prompt. How is the latent image chosen? Okay, so good question. So basically, guys, one thing is that when you are generating, so you need to understand first the training has already happened. So when you are using an application, any application, maybe Dream or any other application, Imagine AI, these applications ask you the prompt and they give you an output, right? So for them, they already have a trained model. So the training is already done. Now, if you look at the structure, I'll just share my screen one more time so that, yeah. Okay. Yeah, so the thing is that this process of training the model that has already happened. So we have already taken 5 so the stability AI, the organization has already taken 5.83 billion pictures and their text embeddings, and they have run the whole training process for those 5.83 billion pictures and the text embeddings to first optimize the weights of this model. Now the weights are already optimized. Now the model is already there, ready to go into the production and generate. Now all it needs is the text representation from here. This input is a seed. This is basically a random noise only, but that random noise is also coming through that seed. You remember in the text notebook also we saw a seed value, right? So basis that number that you provide. So in a lot of applications, you don't see that number because that's a random number. They pick it up randomly only. But in a lot of applications, you would see that they are asking for a number also, a seed also. You input that seed value is defining this latent representation of the noisy picture. Okay, if you don't give it, they'll pick up any random value and create a latent representation of a noisy picture. And the model is already trained, so it takes the prompt, it takes the seed, and it produces a picture. Right? Okay. Yeah, so Shriram BSK, very nice session. Thank you. What is the fundamental difference between the stable diffusion and GANs? Okay. Because as per my understanding, in both the models, we are using UNets. Okay. Don't we have a problem of exploding or reducing gradients here too? Right. So, Shriram, let's just talk about the first part of the question, stable diffusion versus GAN. I think the major difference is that the theory on which they are built. GANs, you basically have two models, right? That we've already discussed. Generator and discriminator both are fighting to optimize their weights, and ultimately, whenever that equilibrium stage occurs, or if it occurs, you take out the generator and use that generator to generate more data, right? This is the core theory, right? In stable diffusion, there's no fight between models, right? It's a diffusion based process where the whole idea is you take noise, you take pictures, you add a lot of noise to it, then you use that data to optimize the weights of a model. That model could be any model. Right now, it is UNet. You could change that model. So stable diffusion has used UNet in their diffusion model, but you can use other models also. And same, UNet is again an architecture. People use it for segmentation also. Now they've used it in the stable diffusion also. It's an architecture that you can use anywhere, right? But the core hypothesis or the core theory on which the whole technology is built is the diffusion process. Adding a lot of noise to the images, then training model that could identify the noise in that noisy picture, and then you subtract that noise from that noisy picture, get a little better picture, then you run that loop over and over again till that time you reach a stage. So it's an iterative process that goes along for a good amount of time. That is why even if you check out the apps, Imagine AI or Dream, it takes you good, I think, if you're not a premium member, it'll take 5 to 10 seconds, right, to generate that, because it's an iterative process. Whereas if you check those apps that we discussed before, which were based on GANs, for them, producing inferences is very fast. Just take a random seed, just take input data, ask the generator to build an output. It's a one-time process. It's done, right? So that is not iterative. So it is fast also, it is lightweight also, but they have other challenges. They are not diverse in nature. Stable diffusion is very diverse in nature, but the problem is that it is iterative, so it takes some time, right? That's the difference, right? Okay, guys. Yeah, I'll share all the URLs of the notebooks that I've used, right? They all are public URLs. You just have to Google Stable Diffusion, Google Colab notebooks. You'll find endless amount of resources on it. I'll share the notebook that I use specifically here. Yeah, I think there are. Yeah, so okay. Yeah, so Nippon has asked why noise is added in steps or in schedule. Can't it be done in a single step straight away? Yeah, so very good question, I think. But I think this is, then we'll come back to that situation where, to the GANs problem only, where we are trying to do everything in one go. See, the thing is, by the way, first, we need to understand how the noise is getting added. Noise is getting added through Markov chain process. You are basically taking an image and you use Gaussian distribution to figure out the pixels, the values that are very common in that picture. You use those values to add the noise. You do it for a repetitive process. And the whole process is built on an idea that every time you run a model, you would want to get to a one step before it, right? So the diffusion model, we saw it has time steps, right? At t is equals to 0, you had the good picture. At t is equals to 1, you had some noise. At t is equals to 2, you had some more noise. At t is equals to 4, you had some more noise, right? The model, this was a forward diffusion process. In the reverse diffusion process, you are trying to predict the noise, right? So the model is built in a way that at any timestamp, you are trying to predict the noise that was added in the last step. So you are predicting some part of the noise. And this is the strong point in favor of stable diffusion, that you are trying to predict some part of the noise. And that you are iteratively doing over the time. And then you are finally coming up with a picture that looks good. To do all of that in one go is very difficult. And then we would end up in the same situation. This is why GANs are not so scalable also. You treat GANs for a specific use case and not able to do all of those things. And it is actually difficult. Like, you trying to get a good image from a noisy image in one go. That's a very difficult problem to solve, rather than let's just figure out the noise that was added from t-1 to t. And let's just focus on that. Whatever you get, then you run it one more time, try to reduce some more noise to it. So that's how the iterative process helps in getting over this, getting a good art from stable diffusion. Yeah. Cool. I think we're good with the questions.
Yeah, sir. Thanks a lot, Akshit sir. On behalf of Analytics Vidya, I would like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it insightful and hopefully we can conduct more such sessions with you in the future. So LinkedIn profile of Akshit sir is there in the chat section. I hope you guys have filled the feedback poll, and if not, I request you to please fill the feedback poll. If you want to conduct a webinar or facing difficulty in registering, please connect with us at editor@analyticsvidya.com. The recording of the session will be available within 2 days on YouTube channel. We'll be back with you in another session of Data Hour on 18th of Feb. The link is in the chat session. Till then, bye bye and keep learning.
Thank you, guys. Thank you, everyone.